Hi everyone, thanks for checking out this video. Also sorry I haven't made a video in like a really long time. I just finished with grad school and started a new job. So I've been like pretty busy with that, but I think I'm gonna start getting back to the normal routine of making videos. But yeah, so this is going to be a lesson today about R, and this is actually the first video I've made on R. And part of the reason for that is because I'm using R for my new job, and so I'm trying to like myself get back up to speed on it and get in some practice with it. So I'm partly making this video for you guys, but I'm also partly making this for myself to like get in some more practice. But yeah, so this is going to be a video about how to do a linear regression analysis in R. First, the easy way, which is just going to be so easy that it'll just be one line of code. And then after that, I'm going to show you guys how to do it from scratch. So basically doing it the hard way, where you like write out like the actual line fitting code yourself. And I think it can be good to like practice doing it that way too, just because yeah, like R makes it very easy to do it with one line. But I think it's good practice to be able to like write these kinds of analyses from scratch to in order to like really understand what's happening with them. Okay, so I made up this like fake data set to demonstrate on. It's a comparison of people's height to their basketball skill. So height is in inches here, and then basketball skill is a rating from like 1 to 10. Okay, so first, before we do any analysis, let's just like plot this data. So I always start off my R files with this line here just to like clear the environment of any variables we might have, although we don't have any right now, but I'll just like run it to just clear any variables. Then the next thing to do is to read in the data. So this reads in the CSV as a data frame, and then in order to access each column in the data frame, we use the $sign. So in order to get the heights, we say data $sign height, and then we get like a vector object of all the heights. And then same thing for basketball skill, just data $sign basketball skill. And then yeah, we get all these like basketball skill ratings. And then here's some code to plot it. So yeah, this is just going to plot the data. And R is kind of nice because we just get like the nice plot like right in our studio over here. But yeah, so here it is. Looks like it could be fit pretty well with a line, and that's because I purposely made this data to look that way. But yeah, also you guys might notice this like outlier down here, this one data point that's 72 inches tall and really bad at basketball. That's because I decided to include myself in this data set. So this little data point here is me. Yeah, I'm 72 inches tall and very bad at basketball. So that's me right there. But okay. So before we do it from scratch, I'll just show you guys like the very easy way to do it. So yeah, it's kind of nice because yeah, R lets you do this in only one line. So I'll just say like easy way here, and then the easy way is we're just going to say model LM, which stands for linear model. This is a built-in function. We don't even need to like import anything. But yeah, linear model. Our skills vector. And then this like tilde sign, yeah, little tilde sign, and then our height vector here. So yeah, basically this is just saying like the left-hand side of this tilde is the variable that we're trying to predict, and then the right-hand side is the variable that we're using to predict the other variable. So this like data height is going to be our like x value. And then the basketball skill is going to be like our y value. And okay, let's try running this. Yeah, so it works in like a fraction of a second, and we get this nice like model R object here that gives us our y-intercept and then our slope. So if you guys remember, this is just like the y equals mx plus b line formula. So this here is the m, like the slope of that line, and then the this is like the b here, the intercept, And if you guys are thinking it doesn't look like this plot intercepts at -13, that's because the plot is all shifted over, so it's starting at 55. But if you were to take it all the way down to like x equals 0, it would intercept it at -13. So yeah, that's the easy way. Then I'll show you guys also quickly how to like actually unpack this model object to get these fit parameters out of it. So we can say fit b equals, I guess I can say this. Okay, short rant about R. I don't like how this thing here is like the assignment operator. I'd like just being able to use equals. And I think in R you can use equals, and it does almost the same thing as this like arrow thing, but not exactly. So I've just been using the arrows just to be safe. But yeah, I don't like how you have to type 2 keys to assign things. That's a slight complaint about R. But yeah, anyway. So to get our fit B parameter out, we just say model coefficients and then 1. Another weird thing about R is that the indexing starts at 1. It doesn't start at 0. So this is giving us our first coefficient. So, I mean, maybe that's not weird. Maybe it's just like every other programming language is weird starting at 0. But yeah, R, it's like MATLAB. It starts the indexing at 1 for these kinds of like list array, like vector type objects. But yeah, that's how we get out the fit B value. And then the fit M, remember our slope, that's going to be the second value here. So yeah, we can run that and then say fit B, yeah, like -13, fit M, 0.27. Okay, so let's now try plotting this. So I'm going to actually just copy and paste in a little bit of code to plot. So yeah, this is what I've been doing to plot lines in R basically. So I'm just saying like the fit X, this is basically just going to be X values. It'll be the same as all of our height values, but it's going in increments of 0.1. So I'll just show you guys what this looks like. It's basically going from the minimum height we have to the maximum height we have, but it's giving us an X value for like every 0.1 in between that range. So yeah, I'll just kind of print out what it looks like. Yeah, so basically going from like 56 to 86, but it's giving us like these little 0.1 sized increments there. Okay, and then the fit Y is just going to be the fit X times the slope plus the intercept. So basically just applying the line formula to every X value you have to get a Y value. Yeah, so now we have the X values for the line and the corresponding Y values, and then we can do a plot like this to plot the line fit. Yeah. Oh, also one more thing to show you guys. If you say summary model, you can get some more information. Like you might want to look at like your R squared value. Yeah, so adjusted R squared is like 0.7635. So that's like a goodness of fit measure. It basically means that like 76% of the variance is explained by this linear regression model. But yeah, it's like higher means it's a better fit, and lower means it's not as good of a fit. And when we do it the hard way, I'm going to show you guys how to calculate the R squared like from scratch too. Okay, so that was the easy way. Yeah, again, super easy, just like one line of code here. Super easy. But yeah, now just for practice, I'm going to show you guys like how to do all this from scratch if you had to. And again, I'm not saying that you should do it from scratch like for a real project or for like your job or something, but I think it's good to, even just for practice, like in the past week or so, I've had to like brush up on R for my new job, and I found it helpful to just like do some of these things in scratch just for practice, to practice with like writing functions and like kind of just knowing how to do things like the hard way if I had to. But yeah, okay. So if you guys have watched any of my other videos, basically the way we do a linear regression like from scratch like this is that we're going to define a loss function that measures, it basically takes guesses for the parameters M and B, and then it basically calculates like how far off all the data points are from our line, and returns like the square of all of those. They're called residuals. The square of like the residual for each data point. It's going to add all of them up and then return that as the total loss for that parameter guess. And then we're just going to guess a bunch of parameters and then find the parameter values that give the lowest loss. So yeah, that's kind of the idea here. Is we're going to define like a loss function to measure how far off our model is from the data, and then minimize that loss function to get the parameter fits. Okay, so I'll just say up here, loss function. Okay, and then loss function equals, although it's not really equals, it's this this arrow thing. Function, guess for M, guess for B, our X data, our Y data. We don't really need to put that because these are already going to be like global variables. But I'm making it this way so that you could pass in like any kind of data vector you want. Okay, brackets. We're going to start off defining our loss as as 0. Okay. Now for this part, we're going to iterate through all of our data points. So I'm going to say for I in starting at 1 going to length X data. That's giving us an index value starting at 1 and going to the size of our data vectors that we're working with. Okay, so now we need to figure out our predicted Y using the X data point and then our guesses for the linear model. So I'm going to say predicted Y equals M. Remember, that's our guess for M, our guess for the slope, times X data I. That's our real data point for X, and then plus our guess for B. It's our guess for the y-intercept there. Okay, so that's our predicted y value, and I'm going to say squared res for squared residual. So remember, the residual is just how far off our predicted value is from the real y value corresponding to that x value. So this is our residual, and then we're going to square it. So for one thing, to get rid of any negative numbers, yeah. So we're dealing with the squared residuals, and then we're going to add this residual to whatever our current loss is. So I'm going to say loss equals loss plus squared res, and then basically after all this is done, we're going to return whatever the loss is. So yeah, this is like the standard like linear regression like loss function to be working with. Basically, just like it's called like least squared residual, or like sum of squares, you might hear it called. But yeah, basically just like calculating the residual for every data point, and then squaring it, and then adding all of those up. That's going to be our total loss. Whoops, just realized the typo up here. Sorry about that. Yeah, it should just be loss function. Okay, looking good so far. So the next thing we're going to do is we're going to like just numerically minimize this function. And for the purposes of this video, I'm going to do this in like the least clever way possible, just to make it easy on you guys and make it simple, and show you guys that even doing it like the least clever way possible, it still is going to work, and we're going to still get like the correct answer out of it. Actually, just fun fact for you guys, like with linear regression, the way it actually works in the computer is that they don't even do like a numerical like minimization like this. There's like an actual like mathematical like textbook solution for how to solve like linear regressions like this. So most computers, I think, will just do that instead of doing like a numerical optimization. But just for the purposes of this video, I'm going to show you guys how to like just numerically solve it, basically. Okay, so I'm going to say minimize loss function. Okay, so for count in range 1 to say like 500,000. Okay, so we're gonna just iterate through this 500,000 times, and then each time we're gonna need a guess for m. So we're gonna say m guess equals. I'm gonna copy paste a little bit of code here. This is a weird looking function because it looks like it says something else. It looks like it says run if, as if it's like an if statement checking if you should run something. But no, it's actually r unif, like r unif for random uniform. So this is a draw from a random uniform distribution. It's not like an if statement or something. It's drawing from a random distribution in between our min and our max. So I set it to be -20 and then 20. And then n is the number of draws you want. I just want one draw. So basically this line is just taking a guess for m, drawn from a random uniform distribution between -20 and 20. Again, this is like the least clever way of doing it possible. If you were doing it in a more clever way, you might have some kind of like better distribution with some priors or something. But no, I'm just saying a bounded uniform distribution between -20 and 20. Okay, and then same thing for the B guess. I'm just going to say B guess also random uniform draw between -20 and 20. Okay, and then we're gonna generate our loss calculation using these guesses, and then our loss function that we just wrote. So I'm going to say current loss equals loss function. Our m that we're passing in is going to be our m guess. B is going to be our B guess. X data is going to be our vector of heights, and then Y data is going to be our vector of basketball skills. Okay, so yeah, so now basically what we want to do is we want to keep doing this for every iteration, and we want to check if the current loss we're generating with these guesses is the best loss we've seen so far. So we're trying to like minimize this thing, so we want like the lowest loss. And if it's the lowest one we've seen so far, we want to like save the loss and then save these parameter values. Okay, so the way we're going to do this is first we need to check if this is the first one we're doing, because if it's the first one we're doing, there's nothing to compare it to. So we have to just save the values no matter what. So I'm going to say if count equals 1, basically just checking if we're on the first iteration. And okay, if it is the first iteration, we're just going to save whatever we get because we have nothing to compare to yet. So we're going to say best loss equals current loss, best m equals m guess, and best b equals b guess. Okay, so that's if we're on the first iteration, but if we're on any other iteration, we're going to compare the loss to the best loss we've seen so far. So I'm going to say else if, yeah, so here we're basically checking if, if the current loss is lower than the best loss we've seen so far. And if this is true, we're going to update these things. So then we're gonna say all of this stuff again, basically. So if we're seeing a loss on this iteration that's the best one we've seen so far, meaning the lowest loss, then we're going to save that and then save the parameter values too. Okay, and then yeah, we don't need to increment count because it'll be incrementing automatically. But yeah, this is basically it. So so yeah, I think we're good to run this now. Yeah, let's give it a try. So that's just defining our function and then actually running the loss minimization here. Okay, yeah, it takes a little bit because yeah, it is doing a lot of iterations, so it takes a couple seconds. Yeah. But yeah, okay, looks like it went okay. So let's just check what we got for now. I mean, we can see it up here too, but I'll just I'll just type it in. So let's see what our best M we ended up with was. So it's like 0.28 something something. Remember, for like the actual R built-in method, we got 0.279, so 0.284. Pretty close, not exactly the same, but yeah, pretty close. And then best B, we got negative 13.81 81751. And then yeah, for the actual like real R method, we got negative 13.4. Again, it's not going to be exactly the same because it is like a stochastic thing where we're like making guesses. But like the more you run it, if we had set this to be like 5 million iterations, it'll take longer, but it'll kind of converge closer to these numbers we got using the R built-in method. Okay, so let's plot these now. Yeah, let's take a look at actually plotting this line fit that we got. Yeah, again, basically just using the same code we used up here, except this time I'm just yeah, defining the x values and then using our fit m and b values that we got from our own like from scratch method to generate the fit y values. So yeah, I guess we can run this all at the same time. And yeah, so if you can kind of see the red line here, the red line is our fit line for our from scratch method, and then the blue line, which is like almost exactly the same, is the our built-in method fit line. Okay, so last thing, I told you guys I'd show you how to calculate the R squared value like from scratch. And yeah, so the way you do that is that basically the R squared value is basically, it's about a comparison of the loss from the fit line, how much loss we're getting from that compared to how much loss we're getting from like a base model that doesn't have any slope and like only looks at residuals compared to the mean of the data. So basically, we're going to define this like thing called base model loss, and that's going to be our loss function except with zero slope, so just a horizontal line, zero slope. So just m equals 0, b equals the mean of our basketball skill data, and then x data equals our heights, and then y data equals basketball skill. Okay, so if you guys just want to understand this intuitively, there's no slope, so it's just a horizontal line, and it's a horizontal line equal to like whatever mean we have for the basketball skill. So it's like if instead of drawing like a line fit like that, we just drew a horizontal line at whatever the mean basketball skill is. So yeah, we want to calculate the loss for that, and then we want to compare our loss for the line fit compared to this like base model loss. Okay, so now we have some base model loss. Our actual R squared is going to be 1 minus the best loss we got from our line fit. Remember, we stored that in this best loss. So that's our loss from our linear regression model divided by the base model loss. And okay, let's see what we get for that. Okay, so our R squared that we did from scratch is like 0.769. Let's look again at what our R squared was for the actual like real built-in regression model. So summary model. And yeah, the R squared for this was 0.7635. So yeah, again, pretty close, not exactly the same, pretty close. If we'd done this for more iterations, like 5 million or 50 million, it would kind of converge over time towards being like exactly the same as the R built-in model, which I'm pretty sure is just solving it like analytically rather than numerically. But yeah, it's our from scratch method has some like randomness. So of course it's not exactly the same, but it's like kind of close. But yeah, that's all I have for you guys for today. This was just a little bit of practice with R, kind of doing linear regression the easy way and then doing it again the hard way from scratch. Any questions, just let me know in the comments. Yeah, I'm probably going to be making some more R videos, just like partly for you guys and also partly for my own practice with it. But yeah, if there's any like specific topics you guys want to hear about, just let me know and I'll try to cover them. But yeah, thanks for watching and see you guys next time.